Hello everyone, my name is Li Lu. I'm now a research professor of Zhejiang University. This work was done when I was a PhD student at Shanghai Jiao Tong University. It's my pleasure to present our work, VocalLock, Sensing Vocal Tract for Passphrase-independent user authentication, leveraging acoustic signals on smartphones. Now let me begin my talk. Mobile devices are now popular in our daily life and work. Thanks to its convenient mobility and powerful capability, we use the devices to store private information, receive personalized recommendations, and even conduct critical operations. So the user authentication becomes vital to protect the user privacy. Representative solutions include fingerprint, face, voiceprint, and so on. Though these widely employed approaches contribute to improving the authentication experience, they may fail to distinguish a real user from a spoofing replayed video or recording. This inspires the development of liveness verification techniques to enhance the security of these approaches. Instead, recent studies tend to investigate the feasibility of employing human behavior for authentication, which naturally embeds liveness verification. Along this direction, we consider the gradually wide deployment of voice assistant, aiming to authenticating users by sensing the vocal tract instead of the voice print. Existing speaking behavior-based approaches authenticate users in a passphrase-dependent manner, requiring the users to remember the passphrase in each login. Similar situations appear in the text-dependent voice print authentication. This requirement significantly degrades the user experience. Revisiting voice print authentication, we find there are two kinds of authentication manner. They are text-dependent and text-independent. Compared with the text-dependent authentication, text-independent one provides more flexible authentication manner, so it can help to improve the user experience and support a wider range of applications, such as phone fraud detection. Along this direction, our goal is to implement a passphrase-independent authentication by sensing the vocal tract behaviors. So how to implement such an authentication? We seek for the help from the text-independent voice print authentication. These solutions usually employ statistical techniques like Gaussian mixture model. So we further use the principal component analysis on our behavioral features and obtain the following preliminary results. We can find that from the perspective of passphrase, the principal components could be distinguished. And from the perspective of users, the principal component could still be roughly distinct, which demonstrates the feasibility of the technical way. Following the basic idea, we first employ FMCW on acoustic signals to sense vocal tract, including the static, shape, and dynamic behaviors of the vocal tract. We first set the two key parameters. They are the period and the bandwidth as 20 milliseconds and 16 to 24 kilohertz, considering the vocal tract sensing requirement and other practical issues, including the human, auditory, and the device limitation. Then we segment each speaking word with audible voice detection and perform the disturb operation to obtain the frequency difference. In the received signals, except for the targeted signal, there are still the line of sight and other reflected signals, which should be eliminated. By developing the SDFD-based heuristic algorithm and verifying the time of flight, we could eliminate them. After that, following similar solution for text-independent speaker recognition problem, we employ the Gaussian mixture model, uniform background model with the male frequency separation coefficient features to construct the passphrase-independent authentication model. Since using FMCW, we only have the frequency difference features representing the vocal tract. Hence, we design an encoder-decoder structure feature transfer network to obtain the relative MFCC features. Afterwards, we could directly train a GMM-UBM model for the user authentication. Then comes to the evaluation results. In the passphrase-independent manner, our system could achieve an overall 91% accuracy. Compared with other solutions, we find our solution could achieve similar performance demonstrating the effectiveness of our proposed solution. On the other hand, we find the false reject rate are all below 2%, and for 82.7 samples, the users could successfully log in with only one speaking. These results validate the good user experience of our solution. In conclusion, this paper investigates the feasibility of realizing the passphrase-independent authentication and further design FMCW-based sensing solution and the GMM-UBM-based authentication model. Results shows that our solution could achieve competitive performance in both authentication accuracy and user experience. That's all. Thank you for listening.